Hello everybody, and thanks for joining this talk. Today I want to talk about two technologies in which I'm a huge believer that they have the potential to significantly improve the performance and lay the foundation for the next generation of data-intensive or low latency applications in the browser. Moreover, these technologies can also help you as a C++ community to move your existing C++ code base to the web in case of WebGPU or in case of WebAssembly, or in case of WebGPU to move your computations from the CPU to GPU, making use of these massive parallel capabilities of modern graphics cards. Okay, so let me start by delving into what I exactly mean when I talk about data and graphics intensive applications, by giving you an example of one of our Rohde & Schwarz applications. So in this example, you see Sceptor, which is basically a radio monitoring application. And with Sceptor, you can search, observe, and then finally locate known or unknown transmitters. This is crucial, for instance, because you want to find transmitters which are illegally operating on a specific frequency because they're not allowed, because probably they have not a license to do so. And when we look at the user interface, of Sceptor, you see on the left side the components which are responsible for processing and visualizing the so-called radio signals or the spectrum. So for example, on the top of the user interface, you see the spectrum display, and on the bottom, you see what's called the waterfall control. And for example, with the waterfall control, you have on the x-axis specified the frequency, which you want to observe, and on the y-axis, it's basically the time. So you can observe a specific signal on a specific frequency or on different frequencies over the time. Another component, in addition to these two specific components for radio signals, which is one of the key businesses of Rohde & Schwarz, we have also on the right of this user interface a map or geolocation or geospatial control. And there we are displaying and processing location information. So it is common in such a control that we are processing hundreds of thousands or even million vertices or data points in real time, which basically means we try to update our UI every 60 frames or every 60.6, so nearly 70 milliseconds, which puts in high pressure or high demand of the underlying architecture and on the used technologies. So all these components have one thing in common, that they are basically data intensive or compute intensive, and they have low latency requirements, which is basically characterized, in my opinion, by three aspects. The first is you have very large amounts of data, or quite large amounts of data. For example, if we're talking about the map display, there we are basically want to display the full planet data set of OpenStreetMap. Then we also, in addition, as a second aspect, we have a high velocity in the data. So the data are changing very frequently when we are talking about the spectrum or waterfall display. And the third aspect is that this processing and visualization has to happen very quickly. So in the best case, like I said, in real time. And so this is quite demanding and not that easy to do. It's, in my opinion, easy to do. Not easy, but easier to do with native desktop applications like Qt, for example, or WPF. But it's quite challenging to do so in the browser. Oh, sorry, it's not Okay. So the question is how we can also build high-performance, data-intensive or compute-intensive application also in the browser. So how we can reach near-native performance also in web-based applications. And these two technologies, which I want to talk about today, so WebGPU and WebAssembly, can help you to reach that near-native speed. So these kind of technologies really shine in that area of data, compute-intensive, low-latency applications. I would say less in the classic single-page application, but it's compute-intensive, graphic-intensive. These technologies are really promising and can be, significantly improve the performance. But before going into detail into these technologies, let me introduce myself. My name is Markus Tremmel, and I work as a staff software engineer and architect at Rohde & Schwarz, but not in Munich here. I'm located in Teisnach, where we have a steadily growing software development department, with over 100 software engineers right now. And my main work focus there is on the development of high-performance map and geospatial applications. So basically, the right side of the user interface you have seen before, I'm very focused on. I'm also teaching vector data processing at the Deckendorf Institute of Technology, and I'm part-time researching on the next generation of map rendering stack, where I'm also doing my PhD. And part of this PhD research is I try to optimize the full map rendering stack from deploying the data in the cloud up to rendering it on the GPU on the screen. So basically from data to pixels. And these technologies are also important building blocks of my research. And some personal note, I'm really passionate about winter sports. I love to do all kind of winter sports, alpine, cross-country skiing, or ski mountaineering, because I come from what's sometimes referred as the pearl of the Bavarian forest, which is Boddenmais. And there we have we have the Bretterschacht, maybe you heard of, we have the Aber, so a really cool winter sports destination. I highly recommend you, if you have time to, because we have really perfect conditions right now. Okay, so the application so these data compute intensive applications, they are really demanding in terms of performance. And when we talking about performance, the efficient usage of the underlying hardware is one key aspect. And so I want to start to give you a rough overview of what's currently available in modern hardware and how you can use it with modern web technologies. And then I want to narrow it down to talk about WebGPU and WebAssembly in the rest of the talk. So this, for example, is a system on a chip from Apple. So it's the A15 Bionic. There is a newer version, I think the A16 in newer iPhones, but it's basically the same. I've took the slide from the Stanford CS149 course Parallel Computing. Really interesting course. I can highly recommend to watch if you're interested. And what you see here is, for sure, the first thing is we have the CPU. So we have a lot of different CPU cores. But this is the first thing if we are talking about web development, which is a little bit different. I would call it to native development, because in my opinion and what I've seen so far, most web applications or most JavaScript applications are still single-threaded. They are still using just one core, which is mainly fine for a lot of applications, for the classic single-page applications. But if you're really doing compute-intensive stuff, then you can be much more efficient if you're using the rest of this chip, for example. So the first thing is we have multiple cores. Then also each core has what's called SIMD, so single instruction, multiple data, so a special instruction set in addition to the classic scalar instruction, which you maybe all use. And this is quite a powerful feature used in image processing, machine learning, and also in modern databases, like, for example, DuckDB, which is based on the vectorized execution model, which is quite popular these days in databases, and this heavily relies on SIMD. So, and basically with SIMD or vectorization, you can execute more than one instruction in a single cycle. For example, to give a simple example, you can, with AVX 512, you can do 60. You can, for example, add 16 integers at a time. So in one cycle. So this feature is quite powerful, but not really used in the web world today. And then for sure we have the GPU, which is also quite powerful. For example, on this Apple chip, it's on the A16, I think it's about, they have 640 ALUs, but in NVIDIA, in the latest NVIDIA RTX, have thousands of cores or different threads which you can execute. So we have the GPU for doing processing, and then, which is some kind newer in the hardware, which arrived in the last years, but for sure will get more and more popular, is what's called the NPU. So the neural processing unit, or maybe you heard of the TPU, which is the tensor processing unit, which is the name more Google is using. And with this hardware, you can basically efficiently execute general matrix multiplications or vector additions, because this is basically what machine learning algorithms boils down or uses under the hood. So with NPUs or TPUs, you can really efficiently execute or inference machine learning models. Sorry. Okay, and so there's a lot of stuff available now in modern hardware, even on such mobile chips. But the question is how we can effectively utilize these hardware capabilities in the browser. So can we, and how can we? And the first thing is how we can utilize or use multi-threading in the browser. This is maybe more familiar to you, or web workers, where you can parallelize different tasks. Just some thoughts about web workers. So I basically think about web workers. They are not so easy to use, like in other programming languages, like in C++ or in Java or in C#. And because of that, they are not so widespread used in the web world. So I not often see web workers used, or not that much like if you have native application. That may come because JavaScript was designed as primarily or initially as a single-threaded language, and the construct added to this language have some entry barriers or make it harder to use. But web workers, in my experience, so also in this web world, in this map world, are mainly used to offload stuff from the main thread to a worker thread to keep the UI free from responding, so free for interacting to user interactions. For example, if you have a map like Google Maps, and you zoom into the map, the new map data are loaded from the cloud or from the server, and then have to process on a worker, because they have to transfer it in something which the GPU can use. So basically in a triangle mesh, which is called tessellation. But this takes some time. But meanwhile, you can still interact with the map, with the old data, because the processing is offloaded. And then when the processing is finished, it gets transferred back to the main thread. So in my opinion, web workers are more for offloading, less for parallelizing stuff. We have tried a lot of different stuff with web workers, and It may work out for machine learning workloads to get real performance benefits, but in my opinion, in my experience, it's more limited to offloading stuff and keeping the UI free for responding. And then one of the topics I want to talk about today is WebAssembly. Because WebAssembly is the only possibility in the browser how you can access this powerful SIMD or vectorization feature. Some years ago, the plan was to add it to JavaScript, but the plans were cancelled because WebAssembly should arrive, and these features were only integrated into WebAssembly. Okay, then the next thing, the next topic is how you can access the GPU from the web. That's also not that easy. So I think it was at the end of 2011 where WebGL arrived in the browser. Before that, you had no possibility to execute code, so-called shader code, on the GPU in the browser. For sure, there were these plugins like Flash and Silverlight and so on, but they were a security nightmare and were kicked out. And because of that, WebGL was the first possibility to execute code in the browser on a GPU. And this was a real game changer, for example, for map applications, because if you're thinking about Google Maps, now it changed from pre-rendered images, like you know it in the old days of Google Maps, where you just transferred rendered images from a server, to transferring raw vector data from the server to the client, and then rendering this vector data in real time on the GPU, which leads to a much better user experience. Like you have much more fluent zoom, you can display 3D buildings, different map styles, and so on. So it was a real step forward where WebGL arrived. But the problem is with WebGL, you can't just basically render an image. You cannot do what's known as, maybe you heard of GPU, so general computations on a GPU. Maybe you know CUDA or OpenCL, for example. This you basically cannot do with WebGL. I talk a bit later about it. There is a hack, which, for example, TensorFlow.js is using, but it's quite a hack. You can't really do efficiently computation on the GPU with WebGL. And 1 year ago, or no, 1.5 years ago, I think in May 2023, WebGPU got officially integrated into Chrome. And now you have first-class support for so-called compute shader, where you also can do computations on the GPU. So you can do matrix multiplication, vector additions, and so on, and return again the data back to the CPU for further processing. So this is a real step forward, also in the mapping world. Sorry, yeah. Oh. Okay, and then finally, there's a new standard coming up. I'm not talking about today, but I think it's also very promising and very interesting because machine learning and AI is getting so much popular and integrating in so much applications. And I think it's very important to have dedicated hardware for the interference of such models, because they have a lot of parameters. They have hundreds of thousands, or millions of parameters. And if you want to do this also in data-intensive applications, you need specialized hardware. And this MPU is the right, or TPUs are the right hardware. And there is this new standard, upcoming standard. It's not a standard yet, but it's very promising, and I think it has to arrive, and it will arrive. This is this WebNN standard, where you can interference deep learning models on such an MPU. Sorry. But this talk today, or just one sentence, WebNN, these are some thoughts we're currently having in our compression. So we're trying to create a new map format, a new worldwide map standard, and there we have to do a lot of with compression and so on. And compression is basically a natural fit with machine learning because you have to find patterns in the data and so on. But the problem is machine learning is doing a really good job. So ML algorithms are doing a really good job in making the data smaller. But the problem is the interference time. So then on the end you have not a net to win because it takes a long time to interference these models on the CPU or even on the classic GPU. And therefore, we have big hopes in WebNN. But the talk today is about these two technologies. It's focused on WebAssembly and WebGPU. Okay, so first I want to go a little bit deeper into WebAssembly. So basically, WebAssembly is an universal low-level bytecode. Yeah, that runs in some kind of a stack-based virtual machine. And that's always claimed that it runs at near-native performance. I have a separate slide for this because this is quite controversial. But yeah, some key idea, and if you read a lot of different blog posts, yeah, this speed or performance is a quite important topic for WebAssembly. And one main aspect of WebAssembly is you could write it with what's called the WebAssembly text language, but I basically know no one who is doing this. So WebAssembly is more a compilation target. So you write your WebAssembly code in C++ or in Rust, which is, yeah, the most used language, probably for WebAssembly applications, or you can do it in C# with Blazor Wasm, or also in AssemblyScript, which is a TypeScript language. And so WebAssembly, just to give you some insights about WebAssembly, it's quite limited. So you only have numeric data types like integers and floats. And you use then normally library like Wasm bindgen to which provides you this, for example, string data types. And you also have no direct access to the web API, which is a little bit a pain. So you cannot do a fetch or you cannot do DOM manipulation. With WebAssembly, you have to go back from the WebAssembly land to the JavaScript land for this web API, for example, if you want to do a DOM manipulation. But if you have which is a little bit a performance penalty, so a performance overhead, like a syscall, but if you're using the right libraries, it's very transparent to you. So you can write your whole application, for example, in Rust, and then you're using these crates like Wasm bindgen and WebSys. It's then completely transparent to you if it's happened in the JavaScript or in the WebAssembly land. And there are basically 3 reasons why people are using WebAssembly. So yeah, the first is the performance stuff, in particular for data or compute-intensive applications. Then, and this is also the main reason, in my opinion, that you can also use other languages than JavaScript. And the third reason is to migrate legacy or existing newer native apps to the web. Like you see it here on the bottom, a lot of such compute-intensive applications have gone that way. For example, you see here Adobe with Photoshop, then you have AutoCAD, you have Figma, which is also quite impressive. So you have a lot of blog posts out there how they did it. And for example, Google Earth, they all migrated their existing code base to the web based on WebAssembly. So I have not the time in this talk to go really deeply into the internals, but I just want to give you a rough overview that you get some kind of mental model how the stuff is working together in the web world. So you basically start by writing your WebAssembly code. For example, you're writing it in C++ or in Rust. Then you compile it, for example, with the Rust compiler, or in C++ you have mscripten, which is basically then using Clang, for example, and thanks to LLVM, to the LLVM WebAssembly backend, you then get a WebAssembly module. And to integrate this WebAssembly module, you first need like always in the web, you need an HTML page. So you're requesting, if you're then the user, you're requesting this HTML page from the browser. And then in the HTML, you have to reference a JavaScript file. Because you cannot currently not directly reference the WebAssembly module, maybe that's coming in the future, but you need this JavaScript glue code, which is then instantiating the WebAssembly module. It's instantiating the WebAssembly memory, for example, and also the module. You have to do that from your JavaScript code. And then you can call the exported function from that WebAssembly module. So just to give you a short example that you get a basic picture about it. So here, for example, you have a Rust add function. Then you annotate it with this Rust wasm create, which basically exports this function. And then if you're using this, for example, wasm pack and wasm bindchain, then it's quite easy to do. You get an ready-built JavaScript file, for example, this app.js file. Then you have to initialize that module, and then you can call all these functions in the WebAssembly module. So it's if you're using the right crates, it's quite easy to integrate, and it integrates quite good in the web world. Okay, some final thoughts to WebAssembly about the performance, because if I talk to people about WebAssembly, the first things they are relating to WebAssembly is the performance. They want to do it because of the performance. And this is something which is very controversially discussed in the community. So you have some blog posts and some papers which are saying, it's not that fast. It's not, for example, on the WebAssembly page, you have something like it's only 10% slower than a native application. But if you take this paper, there's something like, I think about 40% slower for their specific applications. But if you're taking, for example, TensorFlow.js, they are really seeing a massive speed up if they're using WebAssembly combined with SIMD. They even outperform WebGL on smaller models and are competitive on even large models with executing the code via WebGL on the GPU. So just some final thoughts, how WebAssembly is related to performance. So for sure, it's not a silver bullet for performance. So it's not like you're porting to your application to WebAssembly and will run out of the box faster. There might be some cases, but in general, I don't think so. But what you get for free is normally you have faster startup times. Because like in JavaScript, you first have to parse the JavaScript and creating this abstract syntax tree, and then it takes some time. And finally, if you have a hot pass, you have what's called in the V8 the turbofan, which is then compiling it to machine code, and then it basically runs the same as WebAssembly. But the time from parsing to really optimize code could take some time, and there for sure WebAssembly has advantages. Then you have predictable performance, you have no garbage collections, and you also you're more on the optimized, on the fast path. In JavaScript, it's often a problem if you are leaving the optimized path because you are using, for example, polymorphism, then it really slows down the overall performance of your application. And with WebAssembly, it's easier to be on the fast path. And finally, and this is also, in my opinion, the most promising features and which I have the most hopes for our map applications in the future is SIMD vectorization feature, which you only can use in WebAssembly and not in the classic JavaScript world. Okay, so yeah, time is running out. I go a little bit faster over the second part. So the second part, I want to give you a rough overview over WebGPU. And to do so, I want to first give you a rough overview of a graphics API, because I know this graphic or GPU programming is very a niche domain, which is you're not normally doing as a full stack developer. So basically, if you want to execute code on the GPU, for example, for rendering, your geometries, you have basically 4 graphic APIs available. So there's OpenGL, which is out there since over 30 years, I think since 92, which is cross-platform. Then you have the more recent standard, which is Vulkan, which is also very widely used on Android, which is also cross-platform. And then you have this cross-platform-dependent graphics APIs, which is for Windows, which is DirectX 12 3D, for example, and for on the Apple side, so for Mac OS or iOS, you have Metal. And if you nowadays, so since 2011, 2012, want to execute your render code on the GPU, the only way was via WebGL. And WebGL are basically JavaScript bindings for OpenGL. To be more precise, for OpenGL, or it's a bindings for OpenGL, so which is stands for embedded systems. So it's basically available on nearly every smartphone and on a lot of devices. So it's a subset of OpenGL. But the problem is with OpenGL, it's quite an old standard. And it's not, or the API is not really reflecting the capabilities of modern graphic cards. And because of this, the new WebGPU standard arrives in the browser because it's much better reflects the capabilities of modern GPUs. And it's basically also, it's built on the ideas of, also from an API point of view, on this modern graphic API. So it's based on the ideas of Vulkan, DirectX, and Metal, but in a way that it's easy to use. Because, for example, if you want to do a hello triangle, so some kind of hello world in the graphics world, it takes between 1,000 and 3,000 lines of code roughly in Vulkan to do so. Because in Vulkan you have the complexity is by the developer, and in OpenGL it's more in the driver. So the developer has less capabilities to use the graphics cards. And WebGPU, I think, is a really good trade-off between complexity and a nice and easy to use API. So I think the most of that I already said. And the important part now is with WebGPU, like I already said, it brings these compute shaders to the GPU, which is, you maybe have heard of GPU, so that then you can also execute your computations on the graphics card. And this is quite powerful. So yeah, you have this basic 2 use cases. So in the first use case, which was only covered by WebGL, you can draw 2D and 3D geometries, like you know from Google Maps, so these buildings, roads, and so on. And in the second use case, you now can also do computations like this, for example, this machine learning stuff also on the GPU. There's also a lot of performance improvements with WebGPU compared to WebGL. So it is designed to have less API calls. It will add support in the future for multi-threading, which is also very important because currently in such map applications, we see that this encoding of these drawing calls is quite a bottleneck, and this will be much easier and much faster if this multi-threading feature arrives. And yeah, the last feature, you have this compute shader. I think I already mentioned that. Like before that, in TensorFlow, you had some kind of an hack. You could use a texture to write into this texture and then transfer this texture back from the GPU to the CPU. But now with WebGPU, you have first-class support for these compute shaders, and now you have much advanced features like for synchronization and much less overhead. Okay, to sum it up, also current web APIs provide efficient APIs to utilize the underlying modern hardware resources. You can use WebAssembly to port your existing code base, like your C++ code base, to the web, or to move your computations from the CPU to the GPU. You can use WebGPU and compute shaders. Yeah, that I already told you. And finally, what I have not mentioned is you can combine WebAssembly, for example, what we want to do or currently doing in our map prototypes, to use MapAssembly for decoding of the data, for example, for decoding of the map data, which are transferred from the GPU, from the server to the client, and then transfer this decoded data to the GPU to use these compute shaders to do further calculation, and then use the render shaders of WebGPU to render the final map or the final image. And I think this combination can really lay the foundation for the next generation of such data or compute-intensive application, like the maps in which I'm currently researching on. Yeah, so thanks for your attention, and I'm open for questions, but I think we are late in time, right?
There may be a question.
Yeah, so thank you for the talk. Some slides ago you mentioned draw calls or creating the draw calls being a bottleneck. Are there any affordances for GPU-driven rendering in WebGPU, or maybe there are some planned?
No, currently not. This is also something which we experiment in with GPU-driven rendering, but it's not directly supported with WebGPU. But for sure you could use compute shaders to do some kind of GPU-driven rendering, but it's not like, I think, in the latest DirectX versions where you have direct support for GPU-driven rendering. That's currently not supported in WebGPU. Maybe it's coming, but yeah, currently not.
We have another question.
Okay, now it works. Sorry. Thanks a lot for your detailed talk. And regarding WebAssembly, when you compile the WASM module, sometimes if the applications are really large, the module itself can be quite large. I mean, do you consider, just for my understanding, do you split them into different components? Do you use the component model to split it up into different?
Yeah, so currently we are still in the experimenting phase. It's not, so we are having prototypes right now where this kind of size is not our concern right now. But for sure, it's something, maybe you know this optimization technique to have another allocator or so on, which is often takes often some large portion of the total WASM size. Yeah, but currently I have not really a strategy right now because we are not facing the problem right now in that early stage we are currently.
I understand. So, the only thing is, like, if you have an application that is quite large with maybe not even the size, like if you have different parts of your application, right? You don't want to put them all in the same WASM module. Like, I mean, I have experimented with components where you have different components, and then, all right, thanks a lot. Second thing, I always have issues with WebAssembly is like debugging. Because right now I have a local native application and then a WebAssembly application. They're basically the mirror. So I use just debug locally because I couldn't find any reliable ways to, if you have just a WebAssembly WASM application, right, to debug that.
Yeah.
So is there anything that you also?
No, we have the same problem. Basically, yeah, that's with both technologies. So with WebGPU and WebAssembly, this debugging, it's even harder on the GPU. So if you want to debug something, that's not possible. But we also, it's not that, debugging is quite painful. Yeah.
All right. Thank you.
Okay, thank you.